Okay, we're going to do an example here, and I'm going to go a little bit differently through this example. There's a lot of subscripts and such, so I've actually done the example and I'm going to talk you through it, just give you an overview of it. It's fairly straightforward to follow. We're going to do an example with a bolted connection. So it's a glue lam. You can see the cross section here with two steel plates, one on each side. This example, your homework is going to be similar to part of this example, but be sure you read the homework carefully because this example is actually longer because I check a bunch of other stuff. But I wanted you to have it for your notes. All right. The other, and I will, that's one thing. Since I'm not going to go slow and write everything down here, I've posted this example as a hard copy, so you'll have the full worked out example. Those of you who are in the graduate portion of the class, you're going to work through an example of nailed wood on your own to mix it up a little bit. And you can probably find examples in the internet, or honestly, you just work yourself through the nailed section of the NDS, and it's got the equations, okay? And just do the best you can on that. I will post the full solution for that one as well when I post the homework, but give it a shot. Okay, so if we're going to do this problem here, we've got the two steel plates on each side. There's 6 bolts through the steel plates. I mentioned this briefly before, but the bolts, if the bolts here, they're 1-inch diameter bolts, and that means the holes we would do a 1/16 inch bigger. Okay, so we'll need that when we're looking at areas of this wood section. Glue lam beam, here's the bolt spacing, and they're 1/4 inch thick by 6-inch steel plates. Okay, and the glue lam's 5 1/8 inch wide, 12 inches deep. So it's an axial tensile force here, So I'm pulling this off of the base wood. Not terribly different, other than some of the properties are different and how we handle it. But when you start looking at some of the pull out and things like that, it's not terribly different than what you do for steel. Okay, so again, I've printed this out, so you should have an electronic copy of it, and you can certainly print it for your notes. First thing we're going to do, so with wood, we either have Z, which is the bearing type failures, or we have the withdrawal failures where they pull out. They're a pull out rather than a shear type failure. So these are the shear bearing type failures. So you have two choices. You can use the yield equations that are in NDS. And I should say, before you start looking through this, I'd say pause the video or stop and go back and actually go open your NDS or the one online and just read through, not in great detail, but just understand what is in chapters 11 and 12. Okay, so 11 is the general mechanical connections, 12 are the dowel type fasteners, and then Appendix E, when you look in your code, your NDS code, you'll see like an A, B, C, A and C. A is all the appendices, and then those run A, B, C, D, E, F, G, etc. So you'll be in the appendix here, particularly in appendix, let me grab this one, appendix E. All right, so I'm just pointing that out here on this guy. All right, so you're going to obtain the Z value, which is the direct shear for these bolts as the board and the steel plates are trying to be pulled apart. So I'll call that Z parallel. Instead of using the yield equations, which you'll see if you go through those chapters, they use the equations and make a tool for a table for finding values, and that's going to be quite a bit quicker for most of these problems if you wanted to go through and make yourself a spreadsheet, obviously that'd be the quickest of all after you do it once. For this class, we're just going to do, you're going to have a homework problem on this bolted one, and those of you who are in the grad portion of the class will also have a nailed one. But that's, that's about it. If I have this on the test, it would be pretty specific to a bolted problem, very similar to what we've got here. Okay, so we're going to use the tables from the NDS for grain parallel to the force, because if I look at this thing, the force is in the axial direction, the wood grain is also in the axial direction. All right. Table 12I, which is page 104 of the NDS, gives me the values that I need to start looking for Z in this case. And so much like we've done for everything else in wood, we're going to have a Z prime equal to the Z from the table and then all the C values. So for shear, or I'm sorry, for fasteners, and these are dowel type fasteners, so we're going to be using Chapter 11 for mechanical connections in general, and then Chapter 12 for dowel type fasteners for how we calculate all this stuff. So in Chapter 11, page 66, they've got the equations, in other words, which modifiers you use. And so what we have is, and some of these are familiar from other portions of what we've done in flexure and shear. We've got CD, CM, CT, C sub little g, C delta, CEG, CDI, and CTN. So go to table 11.3.1 and it tells you what each of these are. And then that section proceeds to tell, well, the next section proceeds to tell you how to find those C values. All right, so CD, you can look that one up, page 89, 12.5.1. As we, oops, I should have said D, C delta is next. So if you go to page 89 and open that piece in your code, I'm going to just open this up real quick because I wrote something down wrong, just to make sure. But we need CD is our 1.6 from previous. We've looked at that one before. This is C delta. I think in my mind I just wrote D. Okay, so we're going to have to find this guy, and we're going to have to find this guy, C sub G. All right. Then we'll talk about these other three. Okay, so for C delta, there's two choices. D is less than or equal to 1/4 inch, and then I just get to use C sub delta as 1. If it's a greater than or equal to 1/4 inch, I have to look at three different things. One is the edge distance over what the edge distance minimum would be for C delta, okay, for the easy case. The next one is same deal, but at an angle, but we don't have an angle. And then the last one, so first one's end distance, the last one is the spacing. Okay, so go through, look at these two equations, but essentially our distance to the end is 7 inches. And if I look in table on page 90, 12.5.1a, which is where the C delta description is, and they're labeled A, B, and C, I get 7 times D, and I'm using a 1-inch diameter bolt, so CD or C sub delta 1. I'm going to have to use the smallest of these, so B is not applicable. I get A, I got 1 so far. C, choice C, is looking at spacing. They're spaced at 4 inches, right? So 7 was the end distance. These are the spacing. Bolt spacing is 4 inches. If I look in the table, it happens that 4D is the minimum for C delta equals 1. So 4 over 4, and this one's also 1. So all my choices were 1, and so the smallest is 1. And I did it again with I have to print this over again because I have that wrong twice. C delta is 1. Okay. So we also need C sub G, and C sub G is called the group action factor, so the grouping of volts. If you go in the NDS, it's in section 11.3.6 or page 68, and you will see this equation there. It's equation 11.3-1, and it's a fairly long equation, but nothing too complex. Sorry, I dropped my pencil. Nothing too complex. But in that equation, there are m values, which come from u values, and so you have a couple nested equations here. What we need to get to the u value, which is how we find m, and then finally to c sub g, u value depends on the e value and the a value for the main member and the secondary or the attached member, side member. Okay, so we'll look at these, and gamma here is also in the same part of the code, and it's just given for different types of wood to wood, metal, wood to metal, and etc. Okay. All right, so for the side member, that's the steel. So 29,000 KSI, same as you've had before. The area is the area of the plate. There's two of them. If I look at the main member is wood, if I look up E from table 5A in the supplement, I will get that E value. And then the area of the wood portion is 5 1/8 by 12. So I've got that. S, if I look at S in those equations, that's the spacing in the row. Take the small one, and that's 4 inches. And then gamma is another thing that shows up in that equation. And if you look in the same section, which is this NDS 11.3.6, you look in that same section, it gives you the different values. And we have a wood to metal connection with dowel fasteners. And so this is our equation. Remember, D is the diameter. All right, so I do my calculations and I plug everything in. U of 1.011, which gives me an M of 0.862. N is the number of fasteners in a row. We've got 3 fasteners in a row, all right? All right. And then R sub EA is going to be the lesser of the EA of the side to main and then main to side. So you just take whichever one's lower. Okay, so now I can use the CG equation, which was the large one that we looked at the back page, or there's a shortcut and you can get darn close by just looking this up in NDS table 11.3.6 C, and you get 0.992 if you do the calculation, or around 0.99 if you interpolate on the table. So whichever you prefer. If you're faster at you may have to interpolate on the table, so if you're faster at just plugging and then calculator, that's fine too. The other values that were in here are actually just don't apply in this case. So if I look at table 11.3.1 on page 66, you can see what values those are. I'll get there because so I don't shorthand it wrong. All right, so in this case, this C sub EG, that is your end grain factor. C sub DI is your diaphragm factor, and CTN is a toenail factor. So you can go toenail factor. You can go in and read a little bit more about those, but those don't apply for the case that we're doing. Okay, so our Z prime parallel is going to be the 0.992, the 1.6, those are the two factors that we had in there, times 5720 for the section we have. Then I just multiply, so the Z vector is 9,079. So this is per bolt. I have the capacity of 9,079. With 6 bolts, that takes me up to rounding 54,500 pounds. Okay, so if I'm looking only at bearing, this is my capacity, 54,500. Now, if I'm doing a full design and looking at the wood material options as well, which I'm not asking you to do in your homework, you're just doing this first part we just did. The rest of this is very similar to what you would do in steel design. So let me just talk you through this fairly quickly. These are all in Appendix E, so E2, E3, and E4. They're straightforward, they've got the equations there. We have to look at net section tension, tear out of a row, and tear out of the group. So let's look at this. Well, I've drawn it here. Okay, oops, sorry. So I've drawn it here, and essentially the green is if you break the wood itself, right? So that's the net section tension. Row tear out is the blue. So these two individual rows tear out. And red is the whole group tears out. So this would be that kind of rectangular looking tear out. Okay, so you just work through those different cases. And the equations are in E2, E3, and E4. So in E2, it's going to be the tension F prime sub T times the net area. You've done the tension before. You can find the area. The area that I'm looking at, I've drawn here in this picture. Remember, the bolt hole is going to be the diameter of the bolt plus a 16th. So all these shaded blue areas on the right, that is the net area. And I come up with 89,100. So far, that is bigger than what we already found, so the previous one controls. Now, we go into pull out our direct tension row tearing, row tearing, and that is in appendix E3. And here we add up, and they give us an equation. We look at the number of bolts per row times now the shear FB prime, which you've done before, the T value, in this case, the thickness of the wood section, 5 1/8, and then S critical, which is the smallest S spacing, which is 4 inches. Go into here. I've done F sub prime sub B many times, so you do that same thing for this. And then the row tear out Z prime is going to be 3 bolts per row times the F prime sub B, the width of 5 1/8 inch, and then the 4 as the critical spacing, and then there's 2 rows. Okay, so if I use the 2 rows, I get about 37,500. That's rounded a bit. It's actually 37,515. In other words, it's 18,757 per row. Each row can handle. We'll need that for a later combined equation, so I'm leaving it in that term there. And then finally, the group tear out, appendix E4, and that's where we need those row values. So the group tear out equation is basically the two boundary rows. So row 1 and row n divided by 2. So that's going to be 18,000 per row on the edge row and on the other edge row. And I'll point this on the drawing in a minute. Plus the F sub T prime area of the group net. Okay. So they write this out in the code in words in E4, but essentially this is the adjusted row tear out capacity of row 1. So that's the 18,000 something. N is basically the other edge. So if I'm looking at my member here, the red is the net tear out or the gross tear out of the group. And so where the red line goes through. So it's row 1 and in our case, row 2 is row N, which we've looked at each of those and they're both the same. They're both 18,757. All right, so we just are going to plug those two 18,000s into the equation, but I also need to have the A group net. A group net is net section area between row 1 and in our case row 2. So that's this shaded blue. So that's a fairly simple calculation. And then I go in and I plug into the Z prime GT equation. I get 36,300. That's a lower one that I've gotten so far. So if I go back, I have the first one was bearing or direct shear of the bolts individually, right? And then we had the 3 other basically net tension, a row, single row tear out, or individual row tear out, and then finally the group tear out. And if I'm looking at all these factors, this is the one that controls. And so the capacity is controlled by the group of bolts tearing out, not by shear of the bolts themselves, and that's 36,300. So in your homework, once again, you are only calculating that first number. I'm not making you do the second half, but this takes you through a full connection design, and we'll stop that one here.